Hi, y'all. It's Mrs. Blasky. Here is our video about Unit 4 about solutions. Topic 4.1, basic information about solutions, background information. Most of this should be familiar. These are things that got covered in Gen Chem. So first off, the definition of a solution is a homogeneous mixture of two or more substances. You can say that homogeneous instead of homogeneous. Homogeneous means that those substances are mixed together so that they have the same macroscopic properties throughout the entire sample. Macroscopic properties being things that we can observe with our eyeballs. So meaning that it's the same color all the way through, it's the same texture all the way through. If we took samples out of different sections of that substance, the samples would be the exact same, as opposed to a heterogeneous mixture where we can see differences in those properties, or if we take samples from multiple locations in that sample, then those measurements might be different. We can, in general, refer to the concentration of a solution by calling it either dilute or concentrated. So if you think about using drink mix to make lemonade or Kool-Aid or something like that, if it is a dilute solution, it will not have very much color or flavor. If it is a concentrated solution, it will have much more color and flavor, perhaps too much. But to be more quantitative about it, to be more numerical about it, we use a measurement called molarity. So to calculate molarity, you take the amount of solute in moles divided by the total volume of the solution in liters. Notice that that bottom number, the liters, is the total volume of solution. It is possible that when you add in that solute, it is going to change your volume. So the process through which we make a solution is very important. If you start off with a solid, you would weigh out the mass of that solid you need. You would place it into usually a volumetric flask, which is the exact volume that you need. Add a little bit of your solvent to that. For the most part, our solvent is going to be water. It could be ethanol. It could be something else. You're going to mix that together to make sure that it gets dissolved. And then you slowly add up your solvent to the specific volume that you need. So for example, if you weighed this out, you would not start with 500 milliliters of ethanol and add the solid to it. You'd start with the correct mass of the solid and then add up slowly to that maximum volume. This is just some basic math. The molarity of a solution contains 25.5 grams of potassium bromide dissolved in enough water to make 1.75 liters of solution. So to do this math, we would need to take that 25.5 grams of KBr. We need to convert that into moles. 1 mole of KBr. Go to the periodic table and add up the molar mass of potassium bromide. Potassium has a mass of 39.1. Bromine is 79.9. So we add that up, we get 119 grams per mole of potassium bromide, which gives us 0.21428 moles of KBr. To find molarity, we take that moles divided by the total liters. They said to make a 1.75 liter solution. So that's our total volume. We divide, don't worry about sig figs until the very end. Sorry about the pop-up. And I get a molarity of, let's see, how many sig figs should I keep? I should keep 3. Gives me a molarity of 0.122 molar. Unit can either be capital M for molar, or you could write out moles per liter. Either is acceptable. So this same process is going to work for all of the math dealing with solids. We can also make a solution by diluting a more concentrated solution. So when I get chemicals delivered to me, especially things like acids, they come as a very concentrated solution because it's easier to transport. and it's easier to store. It takes up less space. If I wanted to buy 0.1 molar solutions of hydrochloric acid, I'm going to be shipping a lot of water to me and having to store a lot of bottles in the storeroom, which I don't necessarily have room for. But instead, maybe they send me a 12 molar hydrochloric acid solution. I can always add water to that solution to dilute it down to a lower molarity. So what I would do, I would take that 12 molar bottle of acid from the storeroom. I would pull out a specific volume of that stock solution, put it into a volumetric flask. I would then add water up to the mark to make it a new total volume, or whatever my solvent happens to be, to make a more dilute solution. Now, the cool thing about this is however many moles of my solute I pulled out is the same number of moles of that solute that's going to be in here. If I'm adding water to it, I'm not changing how many moles of solute there are. I'm just changing how much water there is in there. So if I know how many moles I've carried over or how many moles I need, I can figure out how much of that stock solution is going in there. So example number 5 says, how many milliliters of a 12 molar stock hydrochloric acid solution are needed to make 1.5 liters of a 0.1 molar hydrochloric acid solution? So if molarity is moles over liters, I want to make a 1 molar solution. I want to know how many moles I need to do that. If I need to make that solution be 1.5 liters. I do my math. That tells me that I need 1.50 moles of HCl to get 1.5 moles out of a 12 molar solution. 12 molar is 12 moles for every 1 liter. So I take 1.5 divided by 12. That means that I need 0.125 liters of that solution. They specifically asked for milliliters. So I move that decimal point over 3 places, and I need 125 milliliters of that stock solution to be able to make my diluted 1 molar solution. This process of being able to know how to make those solutions gets tested a lot on the AP exam. There's often free response questions that ask you, here's the equipment you have. How would you do this with the given equipment? And so that's something that you need to practice. We also need to be able to draw out what is going on in these solutions. So we need to be able to draw the particulate models. So things that you need to think about when you draw out particulate models. We've been doing this for other things. Now we need to think about it in solutions. Sometimes they want you to show the water or the solvent molecules. Sometimes they ask you not to. So in this case, we're showing a couple things. One thing we're showing that solid sodium chloride. We're showing that those sodium ions are smaller than the chloride ions because they are positive ions. They've lost electrons, meaning that they have stronger Coulombic attractions, pulling in those valence electrons tighter. We also see that it goes from being a solid to being dissolved by showing that those ions are separating. Thirdly, it also is showing the ion dipole attraction between the water and those ions. That since this chloride ion is negative, the positive end of the water molecules is going to be attracted to that. Because sodium is a positively charged ion, the negatively charged oxygen end of the water molecule is going to be attracted to that sodium. So those are 3 different things that we can show with those particulate models. We also can show concentrations. So if we look at this particular diagram right here, it tells us a whole lot about what's going on. So first thing I see is that I only have 2 sodium ions, but I've got 1, 2, 3, 4 nitrate ions. So that's giving me some information about concentrations. I know that I have more nitrate than I do sodium. And I also see that this calcium carbonate is sitting down at the bottom of this beaker as a solid. So I know that that is not forming ions in the solution because it is not soluble. When we're thinking about dissolving substances in water to make solutions, we're going to have to go back and think about our solubility rules, especially the SNAP rule: sodium, nitrates, ammonium, and potassium are always going to be soluble, or compounds that contain those elements and polyatomic ions are always going to be soluble. So when we're looking at pictures of solutions, you need to think about the balance of those ions compared to each other. Which ion should be there in a higher concentration or a lower concentration? Should there be the same number of each ion based on what chemical is dissolving? So we will practice this a whole bunch in class. We'll probably spend a couple days on this. If you've got questions, always let me know, and I will talk to you later. Bye, y'all.